Today we're going to look at the normal approximation of the binomial distribution. Now, to kind of explain where this comes from, let me start with this example here and why we do a normal approximation of a binomial distribution. Well, it says 3% of apples are rotten in some kind of a shipment. Find the probability that fewer than 100 out of 4,000 are rotten. Now, normally, we think of a question like this, immediately we think of using the binomial distribution. The reason being, because if you pick up an apple, it's either rotten, which, strange as it may seem, we would consider a success, or it's a good apple. It's either rotten or good. So what are we talking about here? Well, I've drawn this little histogram, kind of a mini version of it, to show you what we're really looking at. We have outcomes that range from 0 out of 4,000 apples being rotten, all the way up to 4,000 out of 4,000 apples being rotten. Now, this is highly unlikely, hence it has a very low bar in the histogram. And the most likely outcome would be something around 3% of 4,000. That's probably how many apples, more or less, are going to be rotten. So that would be our highest histogram bar. What we're interested in is taking these possible outcomes, 0 out of 4,000 being rotten, or 1 out of 4,000, or 2 out of 4,000, all the way up to and including 99 apples out of the 4,000 as being rotten. So I've shaded in these histogram bars. These are the ones that are the answer to this question. It's their added probabilities. So cumulative probabilities is what we're interested in. So binomial cumulative density function, cumulative from the left, N is 4,000, so trials, there are 4,000 apples we're picking up and examining. Probability of any one of those apples being rotten is 3%, so 0.03. And we want to go cumulative up to and including the 99th histogram bar. Now, once upon a time, not long ago, and I'm going back probably about 3 years now or so, if you took your calculator and you tried this binomial CDF with these numbers being so large, the calculator ran into what we called an overflow problem, meaning the numbers were just too big. It was just too much for these older calculators to try to handle, so you couldn't do it. Now, sadly, in a way, maybe it's good on the other hand, today's calculators can handle this pretty easily. So this whole point is a little bit dated. Technology has kind of overhauled the whole idea of getting around this technical problem using a normal approximation. But you still have to learn it. You still have to know how to do it. So what we do instead, since in many cases, if you have an older calculator, you can't do this. You couldn't do. Of course, if you have a new calculator, then you can do it, but you still have to know how to do it the other way. So what do? Well, we use the idea that this histogram stuff here kind of has a bit of a bell curve shape to it. In other words, suppose I made a normal approximation graph do something like this. Now, say I just sort of worked it out. Let's make this one a little bit higher. Say that's what my histograms all looked like, and these bars here. And I said, well, gee, you know, if I just took this region here, that's a pretty close approximation under my normal curve to all these histogram bars. And that's the whole idea behind the theory, is that this normal bell-shaped graph is, even though it's continuous and the binomial is discrete, there's very little difference between the two. Now let me just show you that with a kind of a magnification, and then we'll go back to this problem here. The area that's particularly important to us is when we get to that 99th histogram bar. what we have is, in fact, something that looks like this. We'll start at 0, and there's our first little bar, and then we have a 1, and so on. And the one that we're interested in is this 99th bar, which, say, goes up like that. Okay? And this is the stuff we want to include. Now, if we look at our normal, might do something like that, whatever the case may be. Very important is this. Of course, the binomial distribution is what we call discrete. It has either 0 or 1 or 2 or 3 successes. It doesn't have all the little numbers in between, whereas a normal distribution is continuous and has all the little in-between stuff. So we have to use something called a continuity correction. In other words, we wish to include everything with the 99th histogram bar to the left. So as far as the normal is concerned, we really want to go to there. See, we really want to go not to 99, which is kind of the middle of the histogram bar, but we want to go to 99.5. And that's called a very important little concept called continuity correction. The idea behind the continuity correction is, as I say, if you want to approximate the area totally up to the 99th histogram bar inclusive, well, the 99th bar kind of goes really to 99.5 on a continuous kind of graph. So that's kind of the idea behind it. So how would we set that up? Well, we're doing the same problem now, but we're going to use a normal distribution to approximate it. We would want to go from the left here. So we go, well, normal cumulative density function. So we'd want to start like way far away to the left. So something like negative 10,000 ought to do the trick. And we want to go up to 99.5, okay, because of that continuity correction. And then we want to put in the mean. Well, how do you get the mean of something like that's normally binomial? Well, we kind of said it before. What would be the average amount of outcomes, the average number of rotten apples in a bin of 4,000? Well, 3% of 4,000. So in other words, 0.03 times 4,000. That's how you get the sort of mean expected number of rotten apples. So what I do is go 0.03 times 4,000, and I'm just going to put that right in here. 0.03 times 4,000, comma. Okay, so I'm just going to write down what the formula actually is on the bottom here. To get the mean, you take the number of samples and the probability of success, and you multiply the two things together. So this is our 4,000 times our 0.03. Now there is a formula for approximating the standard deviation, and I won't try to explain the rhyme or reason behind it. It just works like this. It's the square root of n, okay, the number of trials, times the probability of success, times the probability of failure. So what do I put here after the comma? I don't have room on my board, so I'll put underneath here. Square root of 4,000 times 0.03 times 0.97. And then I close the bracket. And so I can now approximate, and I'll give you the answer here, what it actually is. So we go to our distribution, and we choose a normal CDF, cumulative density, so try negative 10,000, comma, 99.5, comma, 0.03 times 4,000, comma, square root of 4,000 times 0.03 times 0.97, bracket, bracket. And here's what I get on the calculator. This is my normal approximation. 0.0287. Okay. So So that would be our approximated probability of fewer than 100 rotten apples in a bin of 4,000. By the way, in case you're wondering what the actual answer was, which I never actually did calculate, but I can do that now, we can go to our binomial CDF, and we said out of 4,000, and the probability of a rotten apple was 0.03, and we wanted to go up to and including 99. That turns out to be, after a little humming and hawing on the machine, 0.0261. So we're off a little bit. Okay, we're off a little bit, but not too bad. We're certainly in the ballpark. Okay. One really important point is, because of today's calculators being so powerful that they can actually do the exact calculation, which is this one, the only time you want to do the approximation with the normal, the approximation to the binomial, is when you're told to. Okay, that's a very important point. Don't just start using it willy-nilly everywhere. Hey, I'm going to use the normal. I'm going to use the normal. If it doesn't tell you to, then you should get the exact answer using the binomial. Okay, but if it tells you to do the normal approximation, that's how you do it. Okay. All right. Now let me just mosey on to the next important point here. Sometimes the approximation isn't very good. I mean, this one was okay, but sometimes it's not very good at all. And how do you know when? Well, let me just show you by way of a little drawing why it's so lousy sometimes. Suppose you had a trial of only, say, 3 things. So you might have 0 successes. You might have 1 success. You might have 2 successes, and you might have, let's say there's 3 successes over here. Say your binomial distribution looked like that. This is with n equals 3. Now, if I tried to draw a bell curve over that, no matter how careful I was, okay, I think you can see why this is going to be a pretty lousy approximation. I'm just going to shade in all the errors where it's putting too much of an area in. Like, let's say I wanted to find the cumulative probabilities for 0 and 1. Well, I'm going to put this extra amount in. I'm going to put this extra amount in, and then all this junk here. That's a lot of extra junk. That's going to make my approximation quite poor. So here's the golden rule. The golden rule is if the trial number of trials times P or the number of trials times Q, if either one is greater than 5. Now some books use 10, but I've seen it in some books using greater than or equal to 5. That's kind of the cutoff. If you get anything that's less than 5, when you go n times p or n times q, then it's not a very good approximation, and you shouldn't use it. So this is kind of the test when to use the normal approximation. So theoretically, before you jump in and use a normal approximation, you should check n times p and n times q being greater than or equal to 5, and if they are, yippee, go ahead and do it. And if they're not, you shouldn't use it. Okay, let me do one last example, and then I think we've pretty much covered statistics. Okay. All right, in this last example, we're going to say 15% of people watch sports on TV. So the sports guys, we're going to say in our little survey, that's 15% of people. Okay, and then we're going to say, well, suppose we do a survey of 700, and we're going to find the probability that more than 100 watch sports. So find the probability that more than 100 people out of 700 watch sports. Okay, and we're going to say somewhere it would tell us use the normal approximation. Okay, because without that, I would have just gone ahead and done it with the binomial. And I'm going to show you the setup with both. I think it'd be very interesting, again, to compare the exact actual answer with the normal approximation. If I was going to, well, let's go ahead and just draw a picture. I always find that the best way to make sense of any of these distribution questions is to kind of draw a little picture and see exactly what we're looking at. Now, maybe I like to visualize things. Doesn't work for everybody, but I like it. So what we have here is that potentially nobody out of 700 watches sports. Okay, a little probability associated with that. Maybe one guy likes sports, probably more likely. All the way up till we get to potentially 700 out of 700 people loving sports, watching sports, and so on. And then all the other histogram bars in between. So here's kind of what our little histogram would look like. Okay, and put a few more in there to make it look more realistic. Okay, that's about all the realism I want, my histogram here. Okay, so we want to find the probability more than 100. So we're looking at, well, let's say this was 100 here. Okay. And we want more than 100, so we would be looking at the histogram bar that is, maybe I should leave the 100 out of there and go with this one. 101 people out of 700 would be a success. We would consider that, yep, that's the bar we want. Because notice they didn't say 100 or more people. They said more than 100. So as far as on the binomial, you're talking 100 and 101, all the way up to, and you're including all the way up to 700 out of 700. So we want it cumulative in this little region here. This is the area that we want to get the probability of. So how do we do that? Well, we go 1 minus binomial cumulative density function. We have a trial size, n is 700 trials. Probability of success here. Now, what do we do there? Oh, 15%. So 0.15. And we want to throw away, because I'm going 1 minus, so we want to take everything up to and including 100 and chuck it out. So this is going to be the exact answer. Well, let's go ahead and find out what that is. It's very exciting kind of stuff. I know you're probably going, oh, I hurry with that calculator. I don't want to see the answer. Okay, well, wait no more. Here it comes. Pretty good probability of 0.6796. We'll go to 4 decimal places on that. Okay, well that's an exact answer, but doggone it, I never actually did this. So I better do that. Now here's my drawing. I'm still going to go ahead and use my drawing, except now I'm going to superimpose a bell curve over top and say, okay, what do I want on my bell curve? Well, I want to start at kind of 101, but notice that the histogram bar is a half, 0.5, I guess, to the left. It's what we also want to include. So for my normal approximation, I don't want to start at 101. I want to start at 100.5. Okay, that's that continuity correction. And then I want to go up to something real big, like 10,000. And my mean is going to be n times the probability of success. 700 times 0.15. And then my deviation would be the square root of 700 times 0.15 times 0.85. And then I'm going to throw that all in the calculator and see what our approximation does for us. And again, I know you're saying, I just can't wait. I wish he would hurry. All right, I'm going as fast as I can. Whoops. See, that's what I get for rushing. Comma, square root 100 times 0.15 times 0.85, bracket, bracket, and here it comes. Very quick, I might add. 0.6831. Not too bad. It's off just a smidgen, but not too bad. So, there you have it. And that's pretty much the idea of the normal approximation to the binomial distribution.